Okay, so this is a sample question that deals with setting up an experiment. So this experiment is a weird one to find g, the acceleration due to gravity. So what we have here is a cart placed on a incline. I'm assuming it's frictionless because it didn't say it has friction on it. There's a spring, which again, it didn't say. We're assuming the spring is ideal. It has a known spring constant, and we want to go ahead and set up the experiment. So for these questions, what you want to do, first of all, is to get an equation that relates all the variables at play here. So we have a cart, it has mass. There's gravity, so we have g as well. Spring constant k is known. The incline has an angle theta, so we want to relate all those variables in an equation. And then from those variables, we need to keep most of them constant, and then we want to have two variables that change. An independent variable, one that we're going to vary, and then a response variable, or a dependent variable that responds to how we change the independent variable. Everything else needs to be constant to reduce uncertainty. Also, to reduce uncertainty, you can't just pick one data point. You have to run multiple trials for different values of your independent variable. You never just do one thing, plug in the numbers, and get your answer. You have to do a best fit line, use the slope of the best fit line, have the unknown variable be in the slope, and then solve for the unknown variable that way. So the equation that we started off with, we want to get an equation, get it to resemble somehow y equals mx plus b. Dependent variable equals slope times independent variable, maybe not plus b. And then the slope has to have the unknown variable in it, which in this case is g. So what I'm going to do for a question like this is first set up the equation. So I'm going to go ahead, let's do it by hand first, set up an equation, then I'll go through and answer the questions with words after I do that. So I'm going to go ahead and do that right now. Okay, so there's two ways to get the equation that relates to the variables. You can use conservation of energy, which is a bit annoying. So I'm going to use the other way, which is forces. And since this is a forces question I'm doing, I'm going to start off with a free body diagram of the cart. And when something's on an incline, I like to put the incline on the free body diagram as a dotted line for reference. And then here's the cart, and there's three forces here. And we're moving parallel to the incline, so we only care about the forces parallel to the incline when I do F equals ma. The first one is normal force, and again, that doesn't matter. There's no friction, so it's not going to affect the pressing force. And we're dealing with forces parallel to the incline. So one force that does matter is the spring force. That goes directly uphill, and that is parallel to the incline. And then mg is directly downwards. And again, we're looking at forces parallel to the incline, so I have to split up mg into components. Mg cosine theta, that's the pressing force against the incline. That doesn't matter here, because there's no friction. And then mg sine theta goes downhill. That is what matters here. And then I'm going to do some of the forces in the parallel direction, that's that way. And the cart's going to be at rest, so that's going to be 0. And I'll take uphill as positive, so the spring force is uphill, it's positive. And then mg sine theta is downhill, so that's negative. And then spring force minus mg equals 0. So spring force equals mg sine theta, they cancel out. And the spring force here, Hooke's law says spring force is kx. So I have kx equals mg sine theta. Okay, so that's the first thing I need to do. I need to get the equation that relates all the variables at play here. Now what I want to do is get it so it looks like y equals mx plus b. And in this case, I want to have or in every case, I want to have an independent variable and a dependent variable. Everything else should be constant. Well, k is constant because the question says k is a constant spring constant. G is what we're solving for. Also, it's a constant by definition. It's the gravitational constant. So I have three variables here, x, m, and sine theta. I can't keep x constant because that's actually going to change. Both mass and theta, if I change mass or theta, that's going to change x. So x, that's going to be my dependent variable. That'll be my y variable at some point. So I can either vary theta or mass, either one. I guess you could add masses to the cart and vary the mass, but what I'm going to do here, I'm going to vary theta because it's pretty easy to just move this clamp up and down and change the angle of the incline. So I'm going to change theta. So I want to get x on the left side of the equation, because that's my y variable, which is a bit confusing, but x is my dependent variable, so it's on the left side. Everything else goes on the right side. So I have x equals mg over k times sine theta. Okay, so this is in the form y equals mx plus b now. There's no plus b, and that's because, it's pretty obvious, when theta equals 0, when you have a horizontal incline, the spring's not going to stretch, so x is 0. So it does pass through the origin. That's something that matters on the AP exam. They might ask, why does this graph pass through the origin? Well, this one passes through the origin because if the incline's at 0, if it's a horizontal incline, the spring's not going to stretch because there's no gravitational force there. So anyways, on to the graph. I would graph x on the vertical axis, and then not theta on the x-axis. If I graph theta on the horizontal axis, I'm not going to get a straight line. I need to get a straight line, otherwise I can't use the slope. So I'm going to graph sine theta on the horizontal axis. Then when I plot a bunch of data points, I can't just take one measurement. So I want to vary theta, get a bunch of different values of sine theta, and then plot the corresponding values of x, get a best fit line from that. The slope of that best fit line, this is y, equals mx. So this is my slope. So my slope is mg over k. Well, mass is going to be held constant. We'll measure mass, will be held constant. K is held constant. So, and then g is a constant. So my slope, which is constant because it's a line, equals m over k, which I know, times g. So I set the slope, which I can calculate, equal to m over k, which I know, times g, and I can solve for g that way. So now that I have all that established, I know the math I need to do. I know what variables I need to measure, which variables I vary, which ones I'm keeping constant. Now I can go through and answer the question with words. All right, so now for the actual questions. Part A, briefly describe the quantities we're measuring, the symbol used for that quantity, and the equipment. So this is just telling the reader what variables we're using and how to measure them, and what the variables we're using are for the rest of the question. So before starting, I'll go back to the equation that I got. So x equals mg over k times sine theta. Again, x is my y-axis variable, my dependent variable. Theta is my independent variable, and sine theta is my x-axis variable. Everything else is the slope. So it said k was a constant it's given to us. G is what we're solving for. So the other three variables, which are x, m, and theta, I have to have a way to measure. So I have to give a way to measure these three. Theta is an angle. I'm going to call it theta. And I measured an angle with a protractor. So that's the first variable. Next one is a bit complicated. This is the distance that the spring stretches after equilibrium. So I have to make two measurements here, and we'll describe it in the steps. The rest length of the spring when it's not stretched, and then the additional length that it stretches, that's x. So that variable there is x. Measured with a meter stick, it's a distance. And then the mass of a cart, which is capital M, I'm calling it capital M. Any mass, you just say measure it with a balance or a dribble beam balance, something like that. Part B is to go in and describe the procedure. For the procedure, all you do is, for the variables that we said we're measuring, describe measuring them, which one we're varying, which one we're keeping constant. So the first variable we'll talk about is m, because that's the one that's constant. So measure m with the balance, and then keep that constant for the entire experiment. And then for the spring, we're trying to measure the distance of the spring, which is x. That's the distance beyond its original length, so we have to measure the original length first. And then the angle of the incline, we'll measure that. And then x, so that's the distance beyond equilibrium. So incline it to some angle, measure that angle, and then measure the corresponding how far the spring stretches. So let's say it was originally here, and now it stretches here. This is my variable x, the original or the additional length beyond equilibrium. Okay, and I can't just do one variable or one trial, so I have to do, the magic number is 5. Do at least 5 trials. And our independent variable is theta, so vary theta by changing the ramp, so you can adjust this little clamp here, up or down, to change theta. And then record the corresponding value of theta for that incline angle, and then the corresponding next value. And do at least 5 trials. Always make sure you have at least 5 trials to reduce uncertainty. So we reduce uncertainty 2 ways. To reduce uncertainty, there's 2 ways to do it. Keep the other variables constant, so m is kept constant, and then have multiple trials for your independent variable. Okay, so part C says, what do I need to graph? So all these experiments are making a graph and using the best fit line. So we already talked about this one. My graph is going to be x on the y-axis and sine theta on the x-axis. I'm going to use the words horizontal axis and vertical axis because it's confusing having x on the y-axis. And everything else is my slope. So I'm going to graph sine theta for each theta value on the horizontal axis, and then graph x on the vertical axis. That's all C is asking for. D is talking about what information you actually need to determine the acceleration due to gravity. Well, again, when you make that graph, you're going to get a bunch of data points. Again, it goes to the origin. your best fit line, the slope of the best fit line, that's going to be this. So set that slope equal to mg over k. You're going to be able to know m and k. We measured m, k was given to us, and then just set that equal to the slope, and you get g with simple algebra. Okay, so that's the steps. Find the slope of the best fit line, set it equal to mg over k, and then solve for g. Okay, so that's the end of the experiment. Part E is just an additional question here. This one gives a different situation. Now the cart is stretched, it's displaced slightly, and then allowed to oscillate up and down. And this is a graph of the position as a function of time. And this is saying, how would you use this graph to find the mass of the cart? So this is going back to period. So the period of a spring is 2 pi squared root of m over k, 2 pi Mario Kart. So we know k still. K is still known. We're trying to find m here. So this graph, it's a bit weird. It's a damp spring, so the amplitude goes down over time, but there is still a constant period. You can do that from crest to crest. That's the period. So you can find period from the graph, then set equal to 2 pi squared root of m over k and get the answer. Okay, so find the period of the graph, set it equal, and then solve for m. And that's part E. All right, so if you follow the general rule that I did for parts A through D on this question, you should do at least okay on this question on the AP exam. So for the experiment, get an equation that relates to the variables, make sure that there's a way to change one of the variables, make sure there's a way to measure the corresponding change in another dependent variable. Everything else needs to be held constant somehow. And you need to say in your procedure how you're keeping those other variables constant, because that reduces uncertainty. Also to reduce uncertainty, have at least, and say this, use this number, at least 5 different values of the independent variable. Measure the corresponding of the dependent variable. Graph some version of the dependent variable on the y-axis, some version of the independent variable on the x-axis. Have the unknown variable be in the slope of that best fit line, and make sure it's a line. Make sure you have your relationship. So here I graph sine theta on the x-axis, not theta. Make sure your relationship is linear, and then have the slope have the unknown in it. Set it equal to the slope, solve for the unknown, and there you go. So if you follow that general rule, you should get most of the points on this question. So yeah, that's the experimental question.